So I think I'm sharing my MATLAB screen now. Okay, so let's get started with this second part and third part of this homework. So the homework problem was, let's see. Okay, so the problem was given this model, which has a hip torque and a impulsive push off, which is shown here. We want to optimize a cost, which is p squared plus torque squared dt, and there was a step velocity and step length constraint. And so we need to find the optimal solution. So what's the p and what's the torque profile as a function of time? And so some time back, I did the simulation where I tried to do the root finding problem, which is traditionally solved in fsolve by fixing p and finding the initial conditions such that I get a periodic gait. So that's the first part. So that helps me to work a series of problems so I can get to part B. The next step is to actually solve part A, which is now I'm going to assume p equals 0.1. So we already have that solution, p equals 0.1. And then we found the steady state. Now the question, now if you put the torque as a function of time in the code, and you ask the optimization to find the torque, when you fix the p, then the expectation is that it will find the steady solution and give you a torque equal to 0. So it will find the passive solution, passive hip swing solution. Okay. So once we do that, I think that the part B is kind of simple. You just have to add p as an optimization variable, and of course add these two constraints, and you will find the solution for that. So we are sort of working a series of problems of harder and harder difficulty to enable us to get to B. Okay, so now I'm going to go and try to do part A here. Fix P and find the torque as a function of time such that it minimizes torque squared dt. So the code I have from last time is, let's see, script is powered fmincon, and let me just run this. Okay, so once you run this, you get a solution, and that solution is, I don't know what is this. Let me remind myself what this is doing here. It's okay, so it basically gives me X, which is this, the solution from solving the optimization, and X solution is basically the solution I got from F solve. So that was done in the past. So those solutions agree, and that means that we were able to find the passive solution. Okay, that's good. Now, before I actually get started at putting the torques inside this, I highly recommend, and this is a bad practice, I did not do this for the simulation. I highly recommend that you need to get the animation written up and going, because it's very easy to debug something such as a walking or a hopping or running robot by looking at a simulation. It just makes your life so easy instead of looking at numbers and trying to guess what's going on. So first thing I'm going to do is try to create a animation. And once I have the animation, I'll go ahead and put the torques and stuff. So let's see how to do the animation. So here I'm going to rely on some of the earlier code I developed. So this is a powered walker, which was I solved using fsolve. And when I run this, I see that I get animation, right? Okay, so I'm going to take this part and sort of get the animation off from so take the animation code from here and put it over there. That's all I'm going to do. So what I need here is I need to get the call. So I get the Z and T from one step, and then I use animate. Okay, so I need to get this code and this code. So let me go to this and then paste it. See, so I need to get after the optimization is done. So let's see, it should be maybe here. Okay, and I need to change this, of course. This is not going to be one step in this, but this is just a start. Because I got this here. Let me go and copy the animate code. So if I search animate, animate is this. So let me just copy this whole thing, make a new file, paste it. And then it will be a part of this lecture note. So I'm just going to save it here. Okay, so it's saved. And it looks like steps is not used. Let me just get rid of steps. So my call now is won't have steps. Let me close this. Let's go here and then see this. We don't need steps. And then FPS, we can just choose it to be, let's say 20 or 30, whatever, 30. Okay, so walker, is walker defined? Yeah, so it's not a problem. Walker is defined. The only thing I need now to do is to get this one step, send this X to one step. I don't have a one step here though. I only have the simulator here. So maybe I can send it to the simulator. Okay, send my solution. In this case, the solution is X, and what's X? I'm just trying to remind myself what is X. X is time, the state before foot strike, sorry, in single stance and before foot strike. This is ideal. So I need to send in X. So let me send in X. I'm assuming that this is the right thing. Let me see. The simulator actually needs, the simulator needs these things. Just take this, copy it here. This is the reference. I need a X, which is a state in walker. I don't need step. So I'm not going to do, I just need to simulate one step. Right? I don't need the whole step. Okay. So I have that. I think this should output Z and T. And then once it outputs that, okay. Now the issue is it's going to output these things, which I don't want to get rid of. I can just keep them. So those will be the first two things outputted, but I also needed to pass Z and T. So I'm going to try to get Z and T as the third and fourth argument here. Z is the all the states, and T is the all the time spans. Okay, so I need that. So let's just go and work on simulator. Okay, I need to get Z and T. So let's see how to get Z and T. This is where I need to look at how exactly were Z and T defined in my powered walker code. So if you go here, P and T from one step. So Z is the output, and so let's look at the output. So Z is ZODE. ZODE is basically the state for one step. So it's basically two, these are the rows and then all state variables. So it should be the position of stance leg, velocity of stance leg, position of swing leg, velocity of swing leg, and then the heel strike state. I can ignore that. I can just plot the single stance, which is fine. And then this is basically giving me the hip position. So I also need to set the hip position. So let's see how to get the hip position. So this is a code to get the hip positions. Basically gives me the point mass, which is at the intersection of the two lines corresponding to the legs. Okay. Okay, all sounds good. Let me try to get the same thing here in the same simulator. So I need to pass, my output needs to be Z and T. Okay, so let's do it this way. So right now I have only 10. Let me just do 100 so that I have a lot of T spans. So my T will be T span. That's solved. Let's do Z. Z will be all my states. So Z temp. So that's going to be all the states 1 through 4 for the columns, and rows will be all the states which I have in this. This should actually be, let me just make it T, instead of T span, let's make it T10 because that's the output. That will be more meaningful. Okay, so I also need to give it XH and YH, which corresponds to the hip position. So let's see how to get that hip position. So hip position is given right here. Let's copy that. And let's define this. So it's X, H, Y, H. And so that's taken care of. And then this is going to be XH start. I don't need to worry about that. Else sign P temp 1. Okay, I'm guessing this part does something good. Let me just keep it as it is. Okay, so I think this is pass the final state. No, pass all the states. Okay, so I think I'm all set to test this out. I'm going to make it print the solution, which is x. So I have a problem with fmincon simulator. So let's go to simulator. And then I need to extract out L, which is missing here. Say L equals walker dot L. Okay, so that's good. So it looks like the animation looks good and as expected, and everything looks fine. And so with this, let's go to the next part now. Okay, so I'm going to not work on this code anymore because that one gave us the passive solution. Now let's just copy this, make a copy of it, and let's call it so this one basically we have torque. So let me call it fmincon 2. Okay, so as I said, my goal here is to get to introduce the hip torque, still keep p equals 0.1, but introduce the hip torque and see if I can still find a solution which gives me torque equal to 0. Okay, so what I'm going to do is I'm going to use the car problem code, right? This is basically the code from which I started off this powered fmincon. This is my core of everything I developed here was from this code. So I'm going to see how I did this in the car code, and then I'm going to do the similar thing over here. So the key thing here is in the car, if you don't remember, this was basically the car which starts and stops in minimum time. Okay, in that case, what I had was there was these controls, okay, n plus 1 controls. There's a time, and right here is where I actually went from p opt 1 to p opt 2. This is basically integrating from one grid point to another grid point, and then p opt, u opt, and then within here, I need to get the control u from interpolation and apply that. Okay, so those are the things which are missing in this code, and I'm going to try to get those in. So we can just start right over here. Right, just start copying this part of the code and incorporate this. Now, we also need to introduce more variables here. So we have to introduce u opt. In this case, it's 2 to n because the first variable was time. So let's just, I think it might be much easier if we start with programming the talks and then work our way down to this. So let's go here. So introduce more optimization variables and then incorporate the talks in this code and then run the simulation, see what we get. So let's go here and then introduce talks. Okay, so there are bounds on the talks. So let me call them u max or u min equals, and I always suggest that you put very low bounds first, and then you can ramp them up. So minus 0.5 and u max equals 1.5. Okay, and so let's go here and then just do the same thing we've done over here. U min, u max, t opt. So we need to define initial, pick this up, put it in fmincon 2. Okay, here it is. Okay, so t opt, this is our initial guess for the time. We already have that. So this is my time. So I'm just going to use that here. My grid points, I'm not specified here. So let me specify them. Let's do a small value for now, 4. Okay. And then maybe I need to disguise it here. Walker.n equals 4. Okay, so maybe I should call it n equals walker.n. Okay, so that's that. It's a parameter, and then this should be by time. So this space, so u max, u min, rand. Okay, so this basically generates u opt and t opt. Okay, so that's done. Okay, now what I need to do is I need to set the bounds here, lower and upper bounds. So let me just copy this. And that will come just after, let's see, bounds are here. Okay. Okay, let me call that u min. Okay, which I'm using the capital U here, and then u. Okay, I defined the LBUB, so let me just define the same way. U min is this, and u max. Okay, so I got u's. And then I need to initialize them to some value. So I've already initialized that by using u opt. So my initial guess is going to have this, the time, the initial state, and then of course u opt. Okay. So remember that this is basically one variable, ZSS0 is 4 variables, and then this is going to be 4 BFS, and then this is going to be n plus 1. It's useful to keep that in mind. I'm just going to copy this, open a new blank file, and just keep it, just save it. And then I just save this syntax. That way it's much easier to retrieve it later on. Okay, save that. So x0 is that. I specified the bounds. I not still put them. Let me just call it ULB. It's better way of calling it. So u, small u, small u. So let's just put it here. And then, okay, so the state is done. The initial, it's passed here. Now there are two places where I need to add, might have to add it, cost and constraints. Okay, so for the cost, right here, let me just skip that for a second. I'll come here, I'll put it here. But right now that's not more important than putting it in the simulator. So let me just skip that for now. Let's come here, but I need to do exactly this at talk state. Okay. Now here I need to, the simulator has X. So I need to unpack U now. U opt is basically X, and we can go through this. So it's basically the 4, so 1, 4, 5 plus 4 is 9. So 9th, so it's going to be 10th variable and goes all the way to n plus 1. So let's say that n is 4. Let me just increase this font. Okay. If n is 4, then we'll have 4, 4, 4, and then it will be 5. So in this case, the indices would be, for the first one, it's going to be 1, next one will be 4, so it'd be 9. So it'd be 10, all the way, so 10, 11, 12, 13, 14, 1, 2, 3, 4, 5. So it'll be 5 controls, 1, 2, 3, 4, 5. So the formula seems to be 10 to n plus n is 5. So it looks like it's 10 plus n minus 1. That seems to be the formula. So the u index, to get the u index, I need to go from n to 10, n plus 1. 10 plus 5 minus 1 is 4. That looks right. So that's my formula. Okay, that's u opt, but it doesn't quite recognize n. So let me just define n. So n is from walker.n. Okay, now u opt has to go as an input to this. Also, t opt needs to go in input. So let's just look at this code where I actually develop code for calling this. So this is what I want to emulate. So let me copy this. this is my code, which I'm going to emulate. And I need to go basically topt. So let me just call it the same as this, topt equals, let's just copy this. I just need to put capital T as time. So it's the only change I need to do. All that time. And then I need uopt, which I already have here. So let me just put it down there. So this is we got rid of that. And now tolerance is already defined, so that's good. So I need to go, I need to have this loop for I equals 1 to n. And I need to do this. So let me just copy paste that. In this case, it's single stance, that, and then topt I, and then it should be z. Okay, so now the initial condition keeps changing. In fact, I need to set that up to, so initially, my initial condition is zss0. Okay, so now the initial condition is right, options is right. I need to pass Walker also here. I did not do here, and topt. Okay, so this is my, it's going to comment this out, so it's an easy reference. I think I'm emulating this code pretty well. So I think I've taken care of all things here, but keeping that in mind. Okay, so now I need to set the initial condition next. So that initial condition will be ZZ temp n, which is right. And the T would be, and I also need to save the state. So I need to do this. Okay. In this case, let me just call it what it was supposed to be here instead of defining it ZZ. So let me call it Z temp, and then Z temp, and then T temp. So there's a continuity, and I don't have to change many things later on. Now, there is one thing though here. I need to look at something else over here. I think I initialized them this way. So let me just initialize the same way as it's initialized over here. And take this and paste it here. And then this is, I would call that C10. And A0 is fine. And then Z is, like this should be before that, and you should initialize Z0, then it goes there. And then it just basically now, when it integrates, just keeps adding this and makes the whole thing ready. So I think that's about it. Okay, I need to get rid of this 100. This was cool. Okay, and now I think I'm ready to go for my cost. Let me go to the cost here and get uopt first. And then if I want to do sum of top square, I can just do so it will be sum uopt, or you can always check. So if you, then if you want to do I think this is a sentence. This looks right. So this is now. Oh, this is right. And then I can sum answer, which is this. I get 14. Okay. So that, and then I think it was times dt, and dt is the time interval. So I just need that too. So let me get that. So the time is the first value, and then I need to get n, walker.n. And then since it's a grid, so dt would be time divided by, it's either n plus 1 or n. How do I check? Well, if you do t equals linspace 0, 1, and then if I do 4 plus 1, where n is 4, then I have this thing, so 0.25 all the way to 1, and it's obvious that dt here is 0.25. So how do I get dt? Well, I need to do 1 divided by 4, 0.25. So it means that I need to take n. So I just need to do time divided by n. Okay, so that's dt, and I just need to do some dt times dt, and then that's my f. That's the cost. Okay, F is 0, it's not 0. Okay, it's complaining. Okay, so I did a lot of programming here, and it's fine to do that, but the other way to do it is to actually do things slowly, one at a time. Add up one thing and check. Here, we just can't. I don't have the luxury of doing that. At only so much time. So let me just run this and hope that it works. If not, I'll debug it. Okay, and this is what I expected. There'll be something wrong. Okay, so let's see. So I think I now remember that I forgot to send those extra arguments in Walker. I have T op, U op, but I couldn't quite send it. So let me see where that is. So that should be in line 142. The T op, U op. Okay, so that is basically this part of the code, which is single stance. I only have TC Walker, but really what I need to do is I need to have T op, U op. Now the problem here is that if I take this single stance file and modify it, it will be incompatible with my first file, the powered Walker fmincon. So instead of using that file, I'm just going to make a copy of it and call that 2. Okay. And this 2 is what I'm going to use, and I'm going to archive the 1. It will be used with fmincon. So this will have to be changed to 2. In fmincon, I need to change this to 2. And now I can pass this extra arguments. Okay. Now, when I pass the arguments, I should see how to use this. So let's go back to this trajectory optimization code. Seems to be the way I use it. This is how I get U. Just copy that. Go here. And then this is basically what I need to do. TH is it's interpolated value between T op, U op. So this is basically gives me the torque based on the U op at that particular time span. So it's integrating from, let's say, 0 to 0.5, and I want torque at 0.25. So it basically use the time t equals 0.25 to interpolate between the torques at 0 and 0.5, and of course, the time corresponding to those torques, and then give me the torque value. So this is good. I hope I'm using the torque here, though. Yeah, there it is. It's been used. So this should work now. If not, I'll just give up. Okay, still there's a problem. It's a different problem. This time it's in single stance 2. Cost. So it started fmincon 2, then it was fmincon. Within fmincon, it was this line 117. Okay. Okay. Let's go dig a little bit more deeper. Constraints, simulator. OD are in single stance. Interp. Something to do with interp. Let's see what's going on in simulator. Okay. This looks right. T opt. Okay, let's look at this code. Did I do anything special here? No, it was this. T opt was that. Okay, so it's something which I don't understand. Let me see. Let me see if the sizes are right. So let's see T size, T opt, size, T opt. Okay, there is a problem here. The sizes are not quite right. T opt is 1 through U. Yeah, I thought I got the right formula here. So let me just print u opt and then print x tend to this basically prints x, it should be the small x. No, this is wrong syntax. Okay, it should be 20. Okay, so 0.15. Okay, so it looks like in my formula I've not done this right. There shouldn't be n minus 1, it should be n. 10 plus n is the right formula. Okay. And then I need to change it here too, because that's where I used it here. N plus n. Okay, let's run this now. Okay, there's a problem here. Actually, I don't need this solution. Let me. Oh, because yeah, so it's now x has more dimensions. It has all the 10 variables. So let me just clip that to the first 9. So 1, 2, 9, right? And then I know that the torque is or u equals x 10 to n, and then I can do plot, and then I can do t equals a linspace 0 time n plus 1, where I think I would I know the n. I just need to tell it what time is. Time is the first variable of my solution. And here what I'm trying to do is I'm trying to plot t versus u. That's my solution. Okay, figure 1 is this. So let me make this figure 2. So figure 1, let me make the figure 1, and then figure 2 can be this. This will be a plot of x label, 9, y label, dot. Okay, so first thing to note is that the torque, if you can see, it's 1e negative 8 versus time. So that's not surprising. The torque should be 0 in this case, because we know that when you have P, when you cannot tune P, you actually get the passive solution. So in this case, do we get the passive solution? It's slightly off. So it's off by a little bit. And the reason is there is this torque, which is contributing to the initial state being not exactly the same. It's still small. I really expected this to be very close to each other. So F value is 0. This is good news. But what beats me is that it just still didn't give me. I expected this to be much more closer. It's kind of off. It's, I would say, way off actually, 0.17, 0.18. It actually stopped at -5, okay. Huh. Let me do something else. Let me go to fmincon options. and look at some of the options I have. So here are the options for Optim or fmincon. So these ones that you see here. So one of them would be display, which is there. And then you can also set some tolerance values. These are the default tolerance value, optimality tolerance, and uh, there should be another one on X, I think, specific. Constraint tolerance, that's another one. That's how good the constraint tolerance should be. Uh, then we just ramp this up to 10, 1e negative 8 and see if that has an effect. So this is 1e negative 6 by default, 1e negative 8. Let's see if that gives me a better solution. Oh, there it is, much better. Yeah, you can see it now. It's looking much closer to the optimum solution, which is close to, that's better, clearly better. So that changed it. Just the tolerance changed it. The other thing you can do is actually you can change the solver. So the default solver is, well, it's SQP, I think, or maybe I'm wrong. And then you can change it to interior point and then see if that gives you a different or better solution. So interior point, you can try that out right away. So we use SQP. I think the default one is interior point. You can just change it to interior point. It's about the same. Solutions are closed. Okay, so I think this is good news because now we got it to converge and give the same solution. You can actually change the bounds here if you want. If you want to really convince yourself, you might want to say, give me both bounds and see if. And then of course we started at 0, right? Let's not start at 0. Let's start at. Well, actually, I did not start at 0, by the way. I started at some random value, not 0. If we give 0, then we know that's a solution. So I started at some random value and right now increase the bounds to just make it harder for the optimization to give me the solution because there's a bigger search range now. And it should probably take more iterations. Okay, so this is going to take a while because this feasibility here it's 1e negative 1. So I'm just going to kill this. Okay. Actually, it's a good practice to keep them low and then keep ramping them if you see that they're hitting the bound. So let's that this works. Okay, so that completes part P, right? So let's go back to this document. So this document, it says uh, if you assume p equals 0.1 and minimize torque square, then you should get a solution which is torque equals 0. We found that's true. Now let's go to the last part, which is the hardest one, right? It's actually quite simple now because we've done most of the work. So I'm going to now actually do one thing. Close this file. Let me call it fmincon B. Okay, just to indicate, A, just to indicate that this is the solution to part A. And then let me copy this and call this B. Okay, so P is here. Okay, now what I need to do here is introduce this P as an optimization variable. So let's just do that. What's going on? My MATLAB seems to have crashed. Let me close this. Okay, let me reopen that. Okay, so the last part, this part won't take me much time, which is probably the simplest one. Okay, let's see if I can do it now. I can do that. Okay, so it's working now. So let me comment this out. I don't need that. That's not going to be, it's going to be a free parameter. Let me put some bounds on P. So P min equals 0. Since you cannot have a negative push off, it has to be 0 for the minimum bound. And then maximum, let's make it 0.5 for now, and then we can ramp it up. Now, when it comes to optimization, I need to choose a value. Let me choose, let me just choose 0 for now, okay? And I could add it after you opt, or I could add it before. I just think it's much easier to add it before, because then it makes it much easier to retrieve it later on, as I'll show you. Okay, so let's put that, and there's a min and a max. So let's just go in here and put the P min and P max. So nothing changes here. What will change though is now this looks right, 2 to 5 looks right. This will change. This will not be 10, it will be the 11th value. And then we'll have, in this case, we will have E equals the 11th, sorry, the 10th value, and then go from 11 to 11 plus n. Okay, so this is going to be some t square plus p. Okay, that's easy. And let's keep going. And right here, we should have, we don't need to do anything here. So let's just keep going right here. So this will become the 11th to 11 plus n. And then p is also an optimization variable, which is going to be p equals x 10. Okay. I think that's good. And the impulse force doesn't appear in these equations. The only place it appears is in the foot strike condition. Now, if you look at the foot strike condition, I can open it. The way I get P is through this walker.control.p. And that's not how I want it. I want it to be passed in variables. So let's just make another file called footstrike2, so that that can be used with this new code, and this file can live with the old one. So let's just make a copy. And paste it here, select 2. And so now I can close this one. So here, P won't be like this. It'll actually be passed as an extra variable. So let's pass that inside fmincon b. So I need to pass this second variable, strike 2. I think that's about it. I don't think I need to do more changes. Okay, now the other thing which I need to do here is to add these things. The step time, let me just look at the document. Okay, I need to add step velocity of 1 and step length of 0.5. So the step length is 2L sine 0.5 theta 2. That theta 2 is the hip angle at foot strike. Okay, so what I'm going to do is I'm going to just define that in the, make the simulator give me that, and then I'll pass it over here. And the reason I'll pass it here, an argument here. So once I have that, I can actually use it in one of the equality conditions. So let me just get that. So right in the simulator, I need to define step length. D step equals T step equals, so T step is just the time, right? The whatever the time is, which is one of the variables. This is just the step time. V step is D step divided by T step. Okay, and then I just need to define this. So this is going to be 2 times L equals walker dot L into sine of 2 times the angle at foot strike. Now, if you go here, let's see this document again. It's 0.5. Okay, that looks right. So let's just go here and then put that as it's going to be ZSST. So we're looking at the first, second, third, the third variable, which is the hip angle. Now, you only have to be careful about the sign here. So the hip goes from, I believe, a negative value to a positive value. So this angle is positive. So this is going to be positive. So I don't have to worry here. So fine. Okay, so I need V step and I need D step. And I need to pass them. So let me just pass them back. V step and V step. Okay, so I can take this. And back here, this is the syntax. So these variables are the 5th and 6th. So there's Z, I don't need it. Let's define the curl. You can define Z and T, but you can also define a tilde just to indicate that you don't need them. And then V step, V looks good. Now I need to use that as an equality constraint. So that will be D step equals, sorry, D step minus whatever that constraint is. D step is 0.5 and V step is 1. 5 is 1. Okay, I think that's about it. Okay, let's run this. It doesn't look like it's converging actually. Exit flag to infeasible point. Okay, there you are. So how to fix this? Okay, let me check if my P is right before I try to do something with the code. P is 10. This is the 10th variable. That's right. And 11%. That looks good. I think this is incorrect. Should be 0.5 theta 2. Okay. Then let me check it. Check it here. Extend. Okay, that looks good. B square, is that the cost I put there? It looks good. Okay, now maybe let's try and see if it works better. Looks like it's doing a slightly better, but it's still struggling. It's so lost. It's going negative and positive. This is the optimality tolerance, which should be 1e negative 8. So I'm going to basically drop this for now. Okay, let me just drop that. Okay, I'm also going to try to go with SQP so that in the past, good luck with that. Okay, now that doesn't rule out some things like there could be a programming error, which is why it is doing what it's doing. So it is. So it doesn't look like, so I need to basically monitor the constraints. So let me just, it's a solver stop probably because it exceeded the limits. But let me just make it print the constraints, okay? So that way I know what the constraints are. The constraints are right here. So I do not care about C, but C quality I'm concerned about. So I don't want this. I don't want this. Let me just get it printing C equality when it's done. Okay, so I changed a few things here. Let me rerun this. Okay. The exit flag -1, that's bad news, infeasible point. Okay, so let's just do this. Let me reduce the bounds. That's the first thing you want to do. I know what, let's not change mess with the human bound, I think it might need that, but let's just change this to, just make it, give it a better guess. 0 is not, it's probably a bad idea, so it's 0.1. And then the bounds, let me just change it to, I don't think 0, we ever get a 0 solution. So we just change that min bound to 0.1. Let's just change this to 0.1 and see what you get. This is something to do with feasibility. It's not feasible. Maybe it's the time. Okay, so maybe it's the time which is a problem because it's hit that limit. Let's go to time and then let it choose. Should I define the min and max on time? So I think it's a relatively faster walk. So I'm going to basically change this to 0.5. So there is a clear problem that it is not quite meeting the constraint here that we can see in the animation. Big flag 2.
It looks like one of your initial points is not within the bounds. At least I think that's what it said on the top. Yeah.
Which of those could it be? I need to put things. So it can't be P, it can't be U opt because those are right now. It has to be the other ones, then this should be these ones. So I need to check these. I really don't think that's a problem normally. So we can check ZSS 0.15, it's in bound, -0.2, it's in bound, -0.3. So this goes from -0.2 to -0.6. That's in bounds. 0 is in bounds of this. Okay, and then BFS. -0.15, that is in bounds. -0.2, it's in bounds. 0.3. So all of them are in bounds. Okay, let me do this. I could potentially use my initial guess from the passive solution. That's another way to do it. So we know the solution. So let's not take this. And use this. Initialize. Oh no, it's still. No, it did not. Z flag -2. This is good. This now you can see that which of the constraints is not satisfied. So the constraint which is not satisfied is basically the last one, and then this is satisfied, and then this one, which is 1, 2, 3, 4, fifth one, fifth one. So we can go to the constraints. This is for the fifth one. That's interesting. This is the 3, 4, 5, 6, 7, sorry, seventh one. So that is basically the something with the hip condition. Third one over here. And then V step is not satisfied. Interesting. I think that I might not be giving it big enough bounds on the angles. Let me just change those bounds and see if that has an effect. So in my lower and upper bounds, I need to modify these bounds. So instead of making 0.3, let me make it 0.4, 0.4. And then this would be so 0.1 to 0.3, 0.4 to 0.1.
Are you starting at time equals to 3 as the initial time?
Yeah, that is, oh yeah, that is the problem. This should be, best way to do it is to do mean of or 0.5. That was the one which is a problem. I think this is the other problem, which is the angles might not be big enough, wide enough for it to actually do that step length. That's why the step length constraint was, step length looks like it's fine. Okay, it's time. The step length constraint looks like it's fine though. This is not used. Okay, why is time not used?
Oh, you specify the initial conditions at the top.
Yeah, if we just take it up there. But now I don't think I'll see that. Let's start it from there. So it's infeasible. So there's some problem with my constraints or bounds. It seems like it stems from this one. That's what I need to hunt for, the speed. V step is 1. Let me decrease it to 0.5 and see if that makes it easier. Nope, that did not converge. Or it did it. -2. Infeasible point. There is probably some coding bug here. It just can't be that. It's not in the solution. It's probably something to do with my coding. Because if you put no bounds on this. Okay, now when you put no bounds in step length and V step, you'll expect that when you minimize this cost, you will try to go for a minimum P and a minimum U, right? So the solution which will come right now will be the passive solution. And the reason why you get a passive solution is because it will choose the minimum value for P, which is 0.1. But then when you choose a 0 value for torque, you should get, so this should give you the passive solution if everything looks right. You can see it's low enough, -10, satisfied. Oh, now I have a problem with the time. Hold on. I need to make this time go up to 3 because it's not encompassing the passive solution. Okay, -7 looks good. Bounds are almost 0. and then the solution looks closed. Now, I can actually close this down by putting the constraint tolerance to be -8. Okay, so okay, I'm past the time, first of all. It looks like the problem is in right there, right in here. This is where the problem is coming. And I think is it D-step? Let me check one thing. I hope this D-step is positive. Cam is going to make it quit after completing it once. So that's good news. It's positive. There's something going on here. Let me just put one of those bounds, not the other one. Okay, the torque is still 0, close to 0. Okay, so now it's trying to take a 3. Okay, okay, so I see. So it's basically giving me an optimal solution. The problem is this constraint. As you can see, if I add that constraint, I don't get a solution. So let me do one thing here now. Here, let me find, let me actually introduce this constraint slowly, right? So point 5 maybe.
Okay, Gonzo.
Yeah.
I remember that on the homework worksheet there was a typo in how you computed. I don't remember, it was a velocity or the step length. Yeah, I think if you scroll down, yeah, the velocity, that should be
Yeah.
d step, right?
Yeah, so D step divided by T step. I think I took care of it here.
Okay.
So if you see here, uh, it's V step is D step divided.
Okay.
Okay, so this is converging for 0.25. This is the solution. So we get -14, and it looks like it's hitting 2. And for some reason, it hit 2. I don't know why. Oh, because of the way it's set up. Okay, 2 is fine. And cost is 0.036, and it found the constraint. So 0.25 is converging. The torque is figure 2, I think. That's the torque. It's very low. Okay, let me ramp this up. Okay, that converges too. Okay, that's good news. Let me pick up this solution. Actually, let me just make it print the solution. Okay, I think let me go a little 5 minutes over. If not, I'll quit for today and I'll debug it later. But let me just get this solution and then try to use that to initialize the initial guess. Okay, so it should have printed X now. That's my X. Okay, let's just make that my initial guess. Okay, so now let's ramp it up to 0.5. Okay, I think I introduced some problem by putting this x0 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What's that? Size X. So 0.5 doesn't converge, but 0.3 converges. I'm going to kill this. Okay, 1 by 15. So I think the problem is I need to give the transpose of that, maybe. Yes, that's the solution for 0.3. Now, the thing which you want to note here is that some bounds are exceeded, 0.5. What's that? So there is something which is hitting a bound. That should be a problem. 1, 2, 3. That's the time. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so I see the problem here. So it's hitting a bound here. Okay. Let's now run this for 0.5 and see if it gives me the solution. Okay, it gave me a solution. 0.99, exit flag -2, which means it gave me an infeasible solution. So let me just go down 0.4 and see if it gives me a solution now. I think it's something to do with the speed. You know what? I think I might know what the problem is. I think I should also modify the speed of the stance leg. It's only the swing leg which I modified. So I need to ramp these up also. So instead of having -0.5, let me just put -1, -1, and let's just make this 2 and 2. Yeah, I think it should work now. Let's go 0.5. Okay. -12. Feasible. Okay, let's go all the way up to 1. Okay, so that's what I got. What I get for, oh, no, it doesn't, it's infeasible, my bad. Exit flag -2. Infeasible. It's probably hitting a bound somewhere. So 0.5 works. It's something to do with the bounds, pretty sure. Okay, let's just change this to 1 and then just change those bounds. Go all the way to 2. 2 3, 3, 3, 3. So now it's hitting a bound on the torques. But then it doesn't look right. Okay, so I think I exceeded my time by a whole lot today. Okay, so what I'm going to do is I'm going to go and debug this, but I think the way to get this solution is to play iteratively with these bounds, and you can always use the solution for one V to get the solution for another V. And now that I've zoomed it down to one single thing, right? So for example, it works when this is removed, it works. But then when I put this V step constraint, it doesn't work. And it does work when you have a low V step, but it just keeps failing at the increased V. So I would just do it systematically. I would go from 0.3 to 0.4 to 0.5 and all the way to 1 and see what the initial conditions are. And once I get that, there might be a deep bug in my code also, which I need to debug if that's the case. And then once you do that, then you can step back and put a bigger bound and get it. So I'm going to stop now, but I'll debug this hopefully and show it to you next time. But I basically got, so first of all, I did this model with a given fixed impulsive force P and no torque, and I found the passive solution. That was a few classes back. Last class, I took the same code and then put torque in the controls and then showed you when p equals 0.1, I get the passive solution, which is passive hip swing solution, which means that torque is 0. And then using that, now I can go to the part B, which is minimize p squared plus torque squared dt, where I impose the constraint of velocity of 0.1, velocity of 1 and step length of 0.5. I've given you the formulas for velocity and step length. Okay, so this is the code as it is from last time. I am going to run this and then go from there. Okay, so first of all, this was for the constraint. Well, first of all, this exit flag was -2, converge to infeasible point. And I think I got this working when this was 0.5 or something like that. Okay, for 0.5 it works. The torques are something like this. This is the equality constraints. They should be close to 0, which they are. This is the solution. And then I don't quite need this. So let me just get rid of this. FL. FL is basically the cost. So let's just go here and get rid of this. And then that's my constraint. That's going to give the solution. And I can actually also make it show the cost. So I can just call this. So I'm going to comment FVAL, which is basically also the cost, but I just explicitly find the cost like this. Cost X. This will give me the cost. And then equality constraints. And then this solution. Okay, so this is basically where it converges because I put 0.5. So let me just ramp it up, 0.6 and see what I get. So let's see the solution. It's this is the equality constraint, so that's E-14. The cost is 0.14. And then this is the solution. If you want to make this slightly better, then what you can do is, in the sense, it say that solution answer equals, instead of that, you can just put it as disp. Then you can say disp. And then this. So this will just, let me just check if this works. Yeah, this works. Okay, so it doesn't show the answer. So that versus this, it gives answer equal that. So if you want to avoid that, want to make it look better, then you can put that. Okay, so this converges for 0.6. So I just keep ramping this up, 0.675. Okay, so now we can see the equality constraints are not satisfied. In fact, it's like minus 0.05 is what you can see. It should be 0, it's minus 0.05. Cost is 0.26. Exit flag is -2, fail. And one of the hints you can get is by looking at the torque. You can see that the torque is, some limit has been reached, 0.5. That seems to be a constraint which is not preventing me from getting the solution. So the best thing I can do is remove the 0.5 constraint. Go up. Where's the Umin Umax? It's not here. That's Umin. So this is minus 0.5 to plus 0.5. Let me make it -1 to +1. And then I'm somewhere printing the size at 1/15. I want to get rid of that. Let me see where that is. I think it's right here. Just get rid of this. Okay. Now I just increase the bounds Okay, so the torque is now, well, it's not, it's beneath the bounds. However, it doesn't look like it's converged to an infeasible point. Okay, so there's a problem here. Is any bound being reached? Doesn't look like so. Okay, that's interesting. Oh. Let me just try to give a generic X instead of giving me the previous one. So this is one of the solutions I got. I used that to initialize the new one. So you do this iteratively to keep a constraint, solve the problem, get a solution, use that to reinitialize for a different constraint. So go from 0.6 to 0.7 and so on. Let's see if this works. This is just giving a different initial guess. Okay, it looks like this worked. So equality constraint is satisfied. Cost is 0.27. This is a solution. Exit flag 1. Okay, so this works for 0.75. Let's see if we can further increase the bounds. Let's make it 0.9. That doesn't look right. So that's not satisfying the bounds. Okay. We go reduce this to 0.8. Okay, now let me try to use this to initialize by 0.9. So let me just take this. And then use this to initialize. So instead of this, okay, so clearly that was a solution. That's why I just didn't do it much. But let's just make it 0.9 now on the constraint. Okay, so looks like it's hitting the bound 1, as you can see. Equality constraint satisfied, cost is 0.47. It's hitting the bound. And actually, you can see it's also hitting another bound. There's a 3. It's unlikely that it's a 3. So let's see what this 3 is. So if you go up there, it's hitting that bound for this. So let me just make it 1.5. So it will not hit that. And then the other 3, it looks like the 3 is coming from, so let's see, that's first one is the time. And then we have the states. So the 4 states, 1, 2, 3, 4. That's the SS0, and then BFS is 4 more states. That's 1, 2, 3, 4. So it's the 4th state in ZBFS. So if you go to ZBFS and look at the 4th state, which is actually the velocity of the swing leg, that's the bound. Okay, so let's just get rid of that. So there is this bound. It's really hitting this bound. But let me just increase that and increase every possible bound here, just because I don't want velocity to be bounded. So we did that, and now we can run this. And now it'll hopefully not hit the bound. And so then we can proceed and go to 1 where we want to go. It looks better. It doesn't hit the bound. Equality constraint 0.46, solution 0.55. Okay. So okay. So now I'm going to now go to the final. Hopefully this is the final time I run this. 1. Okay. This is where we want to be. Run. Okay, so that's it. So that looks like equality cost 0.64. That's the solution. It's hitting a bound here, 0.5, and that bound is actually the time bound, which is actually not a problem. I'll tell you why. So if you look at the time bound, I have a minimum and a maximum. That's hitting 0.5. That's not a problem because the step length is one. I think it's 1 meter, and then the velocity is 1. So the step time has to be 0.5. Sorry, it's 0.5. My bad. It's 0.5 on the velocity and 1 on the step length. So it has to be 0.5. In fact, you can change this if you want 0.3, and you'll see that it doesn't really change. It'll still be 0.5 because that's how the step length and velocity have been specified. You can go here and see that still 0.5. Okay, so I can also perhaps, so this is an initial guess I got from 0.8. What if I get rid of this initial guess? I'm just going to run it from my initial guess earlier, right? So get rid of that and then run this from the initial guess I got from the passive solution, which I think is this. Yeah, this is going nowhere, it seems like. This. One suspicion I have here is that my time bound here, this doesn't make sense because I know it has to be 0.5. So let me just make this, I guess, 0.6 or this means 0.6 because I know it's 0.5 is what I should get. This now. So you can see it's much faster now. So it was searching at a random place. So there it is. That looks very similar to what I got earlier. Equality constraint is satisfied, cost is same 0.64, and then you can see that none of the bounds are exceeded. Okay, so that's looks like that's my optimal solution, which is this is the solution. And then if you go 1, 2, 3, 4, 5, the impulse is this. Impulse is 0.32, and then the cost is 0.64. I don't know, I think Ernesto got 0.76 something, and I think he might have to change some of the bounds, and he should probably hit the solution too, or get a better solution.
I also realized that I didn't square the impulse in the cost function.
I see.
So yeah, that might be why.
We can change that. We can check this with yours. Hold on. Yeah. So the good thing is that you don't want to have p. You don't want to have p square because energy cost is usually impulse square, force squared. But you have to be very careful putting p because if p was negative, then you would have f going 0 or negative. But let's just run this. I think the optimum also might change given this cost. So the solution looks very similar. Equality, so it's 0.85. So you might have got a better solution than me. You got to check. But I get 0.85 versus what you got. And so once you get this, you want to then explore how you can increase this. So you can make it double this. So you remember 0.64 was what I got. As the discretization increases, we will see that the cost will keep decreasing, and at some point it will asymptote. So here it is 0.59, and it looks like it's hitting some limit, right? 1.5, okay, which is not good. So let's just go and change that limit. Well, what's the cost? Let's see. The cost is decreased, okay? So that's good. Let's make that 2. And then I think 8 is fine. Okay, so now it's not hitting the limit, and our cost is 0.59. Okay, so what you want to have to do is essentially here is keep ramping up n, so that way it's not an issue with the optimization. So it's somewhere at certain n, you will see that the cost does not change as you increase n. In that case, you can say that that discretization is fine enough for you to get the solution you want. Okay, so it looks like it's trying to get to the point where it just goes towards this, so it's a sort of a ramp all the way. 0.57. No limits were hit. Okay, let's make it 16 and see if it's getting anyway less than 0.57. Okay. 0.56. That's not a big change. Anyway, so it looks like it's kind of going to be close to 0.55 or so. We can keep increasing, ramping this up to see what that cost becomes. But this is nice now because now it just you can run this code um, for any n. You will also see that as you change the cost function, you'll see that the optimum changes. So that optimum, figure 1, I think, is this figure 2 maybe. This is it's sort of like it's decreasing. So there's a max torque in the start to swing the leg fast enough, and then it just decreases. If you change the cost, and we can actually, well, so if you change, for example, I was trying to see if I can put. Okay, this is a. I don't know if this will work, but I'm going to put a cost which is absolute value, which is actually non-smooth when u is 0. So put abs u opt. Okay, so it's just taking the. So sum abs u opt dt, and then since p is positive, we just put that. Okay, you can see that the solution has changed. It actually starts off at 0, then puts maximum torque in the middle somewhere, not exactly middle, and then it actually holds on to the position for some time. Well, it puts 0 torque at the end. So this is very different from the solution I got when I put torque squared. So as you see that as the cost changes, the solution will change, and so it's very important to put the right cost. So if you care about energy, then usually U square is a good measure. If you care about work, then the cost should be torque times speed. I didn't put torque times speed here. I just put the sum of torque, which is basically saying that average torque should be reduced in some senses. Okay, so let's comment this. Okay, so that's all for optimization. If you noticed, I just did this in a very I did not jump to the final problem. I just tried to solve a series of sub problems with solutions I knew, and I'd highly recommend doing something like this for complex problems because it's just so hard to get some code working from scratch.